Sorry, I pushed the wrong button when I was trying to advance the slide there. The layers, this is a little bit about the ionosphere. Now, when you look at this drawing, you've got the sun up there in the top right, and then to the lower left of this drawing, you'll see the little dark area there. That means sun's not reaching that area. And in that area, what you will see is that the F layer, in the daytime when the sun is on it, it typically splits into two layers where you've got F1 and F2. But at nighttime, once it gets dark and it starts to cool down, the atoms begin to settle down a little bit, they combine back into one layer. Then you've got the E layer and the D layer. Why is this important? Okay, with HF communications, these different layers will carry out certain missions for our communications. Another thing that will carry out a certain mission with our communications is when you look at the line on the Earth here, and depending upon which app you look at how to see it, you'll see a wave imposed on the Earth, and part of it is dark and part of it is light. Well, that line between the light and dark, which is very obvious on the drawing that you're looking at when you look at it, but it's not so obvious on the Earth. But that line is pretty important because that can help your communications as well. So radio waves reflected, typically are reflected from the ionosphere, from the various different layers, depending upon the time of day and the frequency. You can see that the E layer or the D layer does disappear at night. This plays a very significant thing. And your E layer fairly close to disappearing at night. The ionosphere changes with the day to night cycle. This is what this drawing is all about. And you can keep this in the back of your mind as you go through your ham days, and it'll be important. Interesting propagation phenomenon. VHF communications are most often line of sight. Some propagation modes can communicate over long distances. VHF signals may bounce off the E layer. So remember, we said VHF is line of sight. Now we're going to talk about, it's still line of sight, but we're going to use it a little differently. VHF signals may bounce off of the E layer of the ionosphere. This phenomenon is called sporadic E, and it's called sporadic for a reason. You'll have very limited opportunities to use this, and they will typically be short. Phenomenon is called sporadic E propagation because it happens only sporadically. Sporadic E layer allows over-the-horizon signals on 10 meters, 6 meters, and 2 meters. And I would 10, 6, and 2. I wonder if that would extend to 1.25. I mean, it's not a very common band, but I always thought that it would. So 10-meter signals are best in the daytime during high sunspot activity. You get a lot of, for a lot of hams, this is the big thing right here is 10, because it can be long-reaching, very long-reaching during the right times. So sporadic E, let's see. So you see the top layer there is the F layer, and this doesn't really say, I'm going to assume since it's one layer, F, rather than F1 and F2, that this is probably at nighttime. The E, sporadic E layer there, the green layer, and then your D layer is the tan one at the bottom. But your sporadic E would bounce off of that E layer. So anyway, it gives you an example of how the different layers work. These would very likely be different. The green and the blue would very likely be different frequencies. How you doing today, sir? All right. And what was your name? Theodore. Okay. Kruger. Okay. All right. Interesting propagation phenomenon. So we've got F2, F1, E layer, and D layer there, and you see that different signals are coming down, are being reflected down off of those. Some are going to pass right through. Typically, if the angle is too square, okay, too close to being a right angle with the layer of the ionosphere, it will typically go right through. You need to have it so that it's going to glance off at a certain angle. That's not to say that you can't bounce it close to a right angle off of it, because there's actually a propagation method that's I think was discovered by the Army. But anyway, it's short range HF communications. So when you're talking about HF communications, anything that goes out this way is called a ground wave, and you're somewhat limited by that. And then the next communication range with HF is going to be through it's called NVIS, Near Vertical Incidence Skywave, and that'll cover the next range, and there's a gap in between them. And then there's another gap between Near Vertical Incidence Skywave, or NVIS, out to the normal HF communications distance. But you can see higher frequencies will pass right through. Lower frequencies will reflect off of various different layers depending upon what's up there. Which of the following types of propagation is most commonly associated with occasional strong signals on the 10, 6, and 2 meter bands from beyond the radio horizon? Bravo, sporadic E. Why is it called sporadic E? Because it happens sporadically and it bounces off the E layer. Okay. So skywave propagation, interesting phenomenon. So let's see, dipole, 1/2 wavelength height approximately 665 miles for one hop. And remember I told you about NVIS. Sample NVIS, one hop is roughly 102 miles. So you can see there's a gap between their reach depending upon the type of propagation. So there's going to be areas that are dark to you and others that are not. Other interesting propagation phenomenon at VHF frequencies include auroral backscatter, meteor scatter, tropospheric scattering, and tropospheric ducting. I think I touched on tropospheric ducting a little bit earlier. You have something that happens up there and it keeps it bouncing back and forth between a couple of layers until it finally comes out on the end. But all those are different types of propagation. Auroral backscatter, bouncing signals off the Earth's aurora. In the upper atmosphere above both poles, there are donut-shaped regions of charged particles that cause the aurora borealis and aurora australis. This region results from the interaction of solar wind, which is the Earth's atmosphere, and the Earth's magnetic field. Solar wind, the Earth's atmosphere, and the magnetic field. A solar flare can cause the auroral zone to increase in density and expand, making it capable of scattering VHF signals without significant absorption. And does anybody remember what was a couple of months ago? There was, I mean, the aurora borealis was so strong that they were able to see it down into the northern states of the U.S. RF interacts strongly with the aurora. Received signals usually become distorted and signal strength can vary greatly. So, did anybody see the movie Frequency? Yeah, they tried to tie it in with that a little bit. So they had somebody pointing them in certain directions when they were doing that. But yeah, the Borealis isn't going to help you to communicate with your dad who passed away a long time ago. It would be awesomely cool if it could, but it doesn't. Interesting propagation phenomenon. So here's your different auroras. Well, actually, this is both. Actually, I think this is the north on the left and the south on the right. So that's what it looked like when it happens. In that bright, I think it's that bright area, right? That where everything is most active. Right. All right. What is a characteristic of VHF signals received via auroral backscatter? I'm sorry. Bravo. They are distorted and signal strength varies considerably. Interesting propagation phenomenon. Meteor scatter, bouncing signals off of meteor showers. And this propagation is called meteor scatter, most pronounced on the 6-meter band. The 6-meter band is kind of and this is kind of what it's all about, is the meteor scatter. And you're not actually bouncing the signal off of the meteor itself. When the meteor travels through space, it leaves charged particles in its tail behind it, and that's what's causing the reflection. And I have managed to acquire a radio that has 6 meters on it, and I was thinking about building a 6-meter dipole just for that reason, but it's got kind of 6 meters has got limited use, so I haven't done that yet. What band is best suited for communicating via meteor scatter? Bravo, 6 meters, and meteor scatter is being reflected off of what? The charged particles in the tail, yes. Interesting propagation phenomenon. Tropospheric scatter is the lowest region. Troposphere is the lowest region of the atmosphere, extending from the Earth's surface to a height of about 6 to 10 kilometers. Radio waves at UHF and SHF, which is super high frequencies, are randomly scattered as they pass through the upper layers of the troposphere. As the signals pass through the troposphere, some of the energy is scattered back toward the Earth, allowing the receiver station to pick them up. Very limited. Interesting. Let's see, tropospheric scatter. So you can see the way it works there. If your signal, the darkest line is your signal and its trajectory, and the narrower lines, the smaller, thinner lines, are the scatter that happens as it comes in contact with certain things in the troposphere. So you can see the signal is going to be weaker, plus you don't really have a lot of control over where it goes. It's just a luck thing. Tropospheric ducting. Okay. Troposphere is the the lowest region, which we just said, 6 to 10 kilometers. A temperature inversion occurs when a layer of cooler air gets trapped below a layer of warmer air in the troposphere. When this happens, a tropospheric duct may form. VHF signals entering this duct may propagate through the duct for 300 miles or more. It's typically about 300 miles. And there we go. Tropospheric ducting. Super refraction. Signals bend down. Receivers can receive signals from the transmitter. So it's bouncing off of that connection between the warmer and cooler air. What type of propagation is responsible for allowing over-the-horizon VHF and UHF communications to ranges of approximately 300 miles on a regular basis? Alpha, tropospheric ducting, and this one is more reliable than some of the others that we've talked about once it happens, but you have to be able to identify when it's happened. I'm not exactly sure how I did it, but I never did pinpoint what it was. I was on 146.52, which is, it's not a repeater frequency, it's a calling frequency for a 2-meter band. And I got a signal from a guy in Jacksonville. Now, I couldn't reach him back to talk to him, but that's 160 miles. It's quite a ways to reach with the VHF. But he had obviously found something that sent his signal this way. I don't know if he had a directional antenna and more power than I or what. What causes tropospheric ducting? Delta, temperature inversions in the atmosphere, warmer air above cooler air. So typically, the warm air is closer to the ground because it's being, heated by the Earth's mass. And then as you go higher, it gets cooler. Well, when that reverses, you have a temperature inversion, and that's what creates your duct. Precipitation. Rain, snow, or ice can absorb microwave signals, thereby decreasing your range. And remember that with the VHF, you don't have that. It can still happen, but typically not a big effect. Little or no effect on propagation at lower frequencies, 30 megahertz or below. As far as what's below 30 megahertz, besides the ham bands, CB radio is below 30 megahertz also. Microwave absorption. These are different frequency. Okay, so your frequency's at the bottom. Vapor absorption is shown in the vertical axis here. So as the frequency increases, you get a little bit more. What is this modified Rosencrantz? Okay. All right. Okay. What weather condition might decrease range at microwave frequencies? A weather condition that might decrease range at microwave frequencies. And there are bands in the microwave range that you guys have access to, provided you're financially blessed enough to be able to afford that equipment. Charlie, precipitation. What is the effect of fog and rain on signals in the 10 meter and 6 meter bands? So your 10 meter band, well, it's kind of odd because let's go back here a little bit. Little or no effect on propagation at lower frequencies, 30 megahertz and below. Okay, now well, we're not done with it yet. 10 meter band is below 30 megahertz. A 6 meter band is above 30 megahertz. So I'm going to say my answer would be there's little effect. Even though the 6 meter band is 54 megahertz. So, all right, trick question. Takeaways: sporadic E, 10 meters, 6 meters, and 2 meters over the horizon. It is sporadic, and it is given to us with the by the E layer. Auroral backscatter is distorted and varying signal strength. Meteor scatter is created by the charged particles left in the tails of the meteors. And you say 6 meters is best suited for it, and you see that you get 30 seconds to 2 minutes is about the best you can hope for. Tropospheric ducting is refraction off of inversion layer, where you have an inversion of temperature in the atmosphere. Precipitation, which is rain, sleet, hail, and snow, things that slow down neither the mailman nor Santa Claus, but they have a hard time over 30 megahertz. You see it says no effect below 30 megahertz. All right.